So, all right. Okay, so we started discussing, we are doing operational amplifier applications, and last week we started to discuss something called a differential amplifier. We said that you need this in situations where you were measuring, you need to measure some sort of signal or some sort of voltage difference, but that you're not so much interested in what the absolute value of the voltage is, but on the difference of the voltage between 2 points. And we mentioned that, for instance, one particular application of that is in a resistance bridge. If you remember the sort of configuration for a Wheatstone bridge, just briefly, when you were doing it in high school, we sort of had an arrangement like this, right? You powered, you put a plus V or some sort of voltage here, and then you were measuring between these 2 points here. So you had these 1, 2, 3, 4. One of these would have been unknown, but at balance, what you basically have is no voltage here. Right, when the bridge is balanced, you have no voltage between these 2 points. And then at that point in time, you knew something that I think that R1 by R3 was equal to R2, R4, and you could calculate the unknown resistor. The thing with this is that if you notice at this point here is carrying a voltage. If let's say the bridge is being powered by 15 volts. If here is 15, and let's say all of the resistances are equal, just for making an assumption. If all are equal, it means that these 2 points are at least 7.5 volts, right? When they are just off balance, 1 point will be 7.5 plus a very small voltage, and the other one maybe 7.5 minus a very small voltage. So what we say is that what we are interested in is not the 7.5 volts part, but the difference between the two of them. And that's where this differential amplifier comes in. Yeah? And the configuration for the differential amplifier was an op-amp. And we're using both inputs this time because the op-amp has an inverting and a non-inverting input. And we put the differential voltage that we want to measure across the 2 inputs. We have 2 resistors. We have one which is going to the negative input, and we call Rn negative. Of course, the other one that is going to the positive, we call Rn positive. And then there's a feedback resistor between the output and the inverting terminal. And then there's a ground resistor between the non-inverting terminal and ground. All right? And then where we ended last time is to try to evaluate what V out was. And we evaluated V out by using superposition. And remember what superposition allows us to do is to basically, because we are assuming that everything is operating in a linear form, that we could look at the outputs due to one input at a time. So we ground V in. The first one is to ground V in, and then V in plus, sorry. And then at V in minus, we have the output due to V in minus is this one, V out 1. So there's half of the answer here. And then the second part, we ground, instead of this one now, we remove that. In fact, I can erase that. Right? And what we do this time is to ground here. And we put V in plus on this side. And if V in plus is here and here is ground, we can calculate V1. Right? V1 is in fact Vn divided by R2 plus Rg multiplied by Rg. And if you remember, when we were remembering some of the characteristics of op-amps, if here is V1, well, here's V1, here has to be V1 because of the virtual earth behavior. And if here's V1 and this point is grounded, then we can calculate V out, which is, because it's an a non-inverting amplifier, V out 2 is V here by 1 plus Rf over R1. And we know that V1 is this little bit here. Right? So in other words, the output, the second half of the output due to Vn plus is this. The first half due to Vn minus was this. So therefore, if I were to put Vn plus and Vn minus across the two terminals, the total output is the sum of those two. That is because we're using superposition. Yeah, everybody recall that? Anybody had any issue with the derivation? We did it in class and I asked you to look at it if there were anything that, or there was anything that you were not clear on. Right, everybody all right with this, right? It's fairly straightforward. Just a lot of subscripts around the place. Okay, so if you're all right with that, then what we also said is that if I wanted the output to be the exact difference of the two inputs, then actually what I could do, if I made all the resistors equal, if I made all of these resistors equal, so 1, 2, RF, and RG are all equal, then what you're going to have is that this whole factor here becomes 1, and this is also 1. So you get that V out is Vn plus minus Vn minus. In other words, the output is a difference between Vn plus and Vn minus. Yeah? Fair enough? All right, as I say, if you have any questions, well, you need to attract my attention. I can't see the chat, so you'll have to tell me yes or no as we go on. So if all the resistors were equal, then the output is actually just the difference between what you put on Vn plus and what you put on Vn minus. In other words, the difference of the two terminals. Because these two values tend to be very small, typically what we want is to use the op-amp to give us a little bit of gain too. The op-amp is good at that. It has that ability to give us a lot of amplification. So instead what we do is that we make the two input resistors, which we called previously Rn minus and Rn positive. These two here, the two input resistors, we make these equal and we make the feedback and ground resistors equal. And if we do that, then the input-output relationship is that V out is V diff. Remember, this is a small voltage that we're trying to detect. And we put a gain, RF over R. So if this is 100K for argument's sake, and this was 10K, we have a gain of 10 V diff here. All right? We could put it up to 1 meg, we could, and so we can go on. So we could get a reasonable amount of gain on this. All right, once you know what you're dealing with, as usual. Okay, and of course, V diff is Vn minus, Vn plus minus Vn minus. Excuse me for a second. Yes, apologies. So, right, so the output is, in this case, some gain times V diff, and V diff, of course, is the difference between what is going on the non-inverting terminal, the difference between the voltage on the non-inverting terminal and the voltage on the inverting terminal. All right, that's V diff. So usually what the information that we need is contained in that difference. The absolute value of the potentials is immaterial. And if you go back to the bridge that we drew here, right? At this point in time, at the point when the bridge is almost, say, if I were to put the differential amplifier right here, right? Let's say I had it hooked up to this, across this point here. At that point, here is, as I said, at the point when it balanced, these two terminals are at 7.5 volts. I don't care about that. That's the thing about it. What I care is the difference. What I care about is the difference between those two potentials, right? The absolute value of the potential. So that voltage that appears the same, that the value appears at both terminals is what we call a common mode voltage. And that should not affect our measurement because it has no use for us, right? What we are interested in is the difference between the two voltages, between the voltages at the two terminals, right? And again, for instance, in thermocouples and resistance bridge outputs, there are many biomedical applications, as I mentioned, where they use that. And when you're doing biomedical application measurements in particular, your body, because we are in an environment where we are in the presence of a 60 hertz AC power source in the rooms and in the walls and so on, our body acts a bit like an antenna. And if you were to take, for instance, if when you go into the lab, you take a scope probe and you hold it in one finger and you watch it, you're going to see a 60 hertz signal coming out on the scope. It will look something like that. The amplitude could vary depending on how moist your skin is and how and which part of the room it is. But next time you go into the lab, just hold the scope probe, set up the thing and put it like on maybe 1 volt per division, and the time base to allow you to read the frequency, and you will notice that you have this 60 hertz. It's a 60 hertz signal, and the voltage is quite large. If you were to put probes, for instance, when you're taking heart or muscle measurements, those very small voltages, what happens is that the voltage actually, if you watch it on the scope, it actually looks something like this. Right? So there's this big 60 hertz thing. These little fluctuations are what you want. This 60 hertz thing is the common mode signal, and that is what you want to ignore. And the differential amplifier is supposed to do that. How good it does it is by something that we're going to talk about now. Okay, so everybody following that? Any questions so far? All right. So we have the amplifier here, and we have discussed up until the performance up until this sort of line here, right? So we looked at all of that just now and last time, right? So what we're going to do now is let's model the input a bit, right? So we have the two inputs here. We have Vin minus and we have Vin plus. And we say that V diff, or the differential input, is the difference between Vn plus and Vn minus, right? And V common mode, right? Remember that Vn plus and Vn minus might have some signal riding on it. We define VCM, or V common mode, as the sort of average voltage between Vn plus and Vn minus. So like in the Wheatstone bridge that we had before, one of the terminals would have had like 7.5 volts plus some small V. And the other terminal would have had 7.5 volts. Well, let me see, Vn plus, and the other voltage would have had 7.5 volts minus Vn minus. Okay, so that the common mode voltage for these things would have been the average of these two. So if I add the two of them, and divide by 2, I'm going to get 7.5 volts here, right? So we do a little bit of a model. If this is Vn, if this is up to this point, so this is Vdiff, we say we have a common mode voltage, which is this thing that we don't want. And how we're going to express it is that our differential voltage, we have it in two parts. So Vdiff, we split it up into 2 bits here. Okay. So if you ignore this for the time being, Vdiff is composed of 2 things, Vdiff over 2 in value. And then at the junction of the 2 of them, we add our common mode voltage. Remember, this is what we don't want, right? We don't want to measure that. This is what we want. Okay, everybody understanding the little model that I have here right now for the source side of things. The differential voltage, we model it as though it's two voltages added together, and we add the common mode voltage to the junction of the 2 of them. Okay, so if we do that, we get that Vn minus will be V common mode. If you look at it, Vn minus will be V common mode minus Vdiff over 2. And Vn plus will be V common mode plus Vn over 2. If you want to put the polarities, right, just to make it easier, you could put it put it so, okay? So Vn positive is more positive than Vn negative, of course, so that if you want to see Vn positive is V common mode plus Vdiff over 2, and Vn negative is V common mode minus Vdiff over 2. Yeah? We all right with that? Yeah, let me know. Give me some feedback, somebody. One person. 1 out of 61.
Yes, sir. Yes, sir.
There we go. Right, good. So one person acknowledges on behalf of the class. That's democracy. Okay. So the output voltage, we just derived that the output voltage was this. We did this a couple slides ago. Rg, right? Rg over R1. This is this. So this is the part. We did this by superposition, by Vn plus, and a part by Vn minus. And what I'm going to do is to substitute for Vn plus and Vn minus in terms of Vdiff and V common mode. All right. So if I do it, then the slide went a little bit backwards. This is what I had before. Half a second again. Sorry. So this is what we have. This is what we derived a little bit ago. The animation went backwards. And Vn plus, as we said, remember, is if you wanted minus, plus, minus, plus. So Vn plus is V common mode plus Vdiff over 2. And Vn minus is V common mode minus Vdiff over 2. All right. All I've done is to get rid of these 2 things now in terms of 2 things, the common mode voltage and the differential voltage. One we want to ignore. And what I'm going to do now is to expand this equation a little bit and group everything with V common mode together and everything with Vdiff together. Okay? If I do it like that, you will notice that you now have an expression for V out that is part something to do with V common mode and something to do with Vdiff. In other words, the output for this differential amplifier is composed of 2 parts. There's a part that is amplifying V common mode, And notice what the expression is for here. It's essentially the same the same core inside of here. For V common mode, is the difference of these two by V common mode. In the case of V diff, it's the sum of the two, but then then you take a half on the outside. Okay. So already you could see something. If all the resistances were equal, as we said before, if all the resistances were equal, this bit, this section here, and this section here would be equal, 1 and 1. So V out would be 1 minus 1 by V common mode. In other words, if all the resistances are equal, it would ignore this bit, it would ignore the common mode signal. And if all were equal here, you would have 1 plus 1, which is 2 divided by 1, which is 1. Sorry, 2 divided by 2, which is 1. So you would have V out is equal to V diff. So if all the resistances were equal, and remember there's just 4 resistances we're talking about here, if all of them were equal, then the output of the differential amplifier would have just as the output is a differential input. It would ignore the common mode voltage. We all right with that? Everybody seeing that? Yeah?
Yes, sir.
The problem, of course, is that you can never get the resistors equal. All right, if you look at these things, these resistances always have some tolerance. So let's see what's the effect of that. Right, so the gain has 2 parts. There's a part that is amplifying the common mode signal, and we call this particular expression here the common mode gain, AV common mode, right? This is what we don't want. And there's a part that is amplifying the differential signal, this expression here, and we call that the differential gain, AV diff. And this is the part we want. Ideally, as we just said, it should amplify, the amplifier on this circuit should amplify the difference signal and not respond to the common mode signal. And how well it does that is something called the common mode rejection ratio. We mentioned that last time, and this is basically what it is. The common mode rejection ratio for an amplifier is the ratio of AV diff to AV common mode. And as you saw, ideally, this is some number determined by the resistors. Ideally, if all the resistors are equal, AV diff will be 1. If all the resistors are equal, AV common mode is 0. So if all the resistors are equal, the common mode resistor, the common mode rejection ratio should be infinity. Yeah? In other words, a very high number. Most common mode, most op-amps, sorry, when the op-amp is not in circuit, in other words, you haven't plugged it into anything, have a very, very high, what they call an intrinsic, that is not in circuit, an intrinsic common mode rejection ratio. And the value, because the numbers are so big, they tend to specify the number in something in a unit called a decibel. We're going to meet that more and more. But if you remember from even physics, I think you should have, a decibel is 20 log to the base 10, usually of a ratio, some 2 numbers, N1 over N2. All right? So like the common mode rejection ratio is the ratio of AV diff to AV common mode. And because it's usually a very big number, they express it in decibels, which is 20 log to the base 10 of that ratio. Typically, like even an inexpensive op-amp, like the 741 op-amp that you met in level 1, a general purpose op-amp that costs maybe 10, 15 cents US. Even that by itself, without doing anything, you just rest it on a piece of paper, as the manufacturer gives you it, has a common mode rejection ratio of about 80. So if you were to make a differential amplifier and you had resistors that were identically equal, then this thing, the ratio between what it would amplifying what you want, which is this, and not amplifying what you want, which is that, is going to be 80 decibels or more. If you want to find out what the number is, the actual ratio, divide this by 20. So that's 4. And what is 10 to the power 4? Well, 10,000, right? 10. So in other words, even something like a 741 op-amp, if you were to able to make a differential amplifier and get all the resistances equal, it would amplify or discriminate between the differential voltages and the common mode voltages by a factor of 10,000, 10 to the power 480 dB, right? And again, if you want to just express it in terms of what we did there, the output voltage is a differential gain by the differential input plus the common mode gain by the common mode input. This is supposed to be small. This is supposed to be 1 or better. We determine that. Right? So let's see what happens now if you're in a real situation. So you have an op-amp, and the op-amp, as you buy it from the manufacturer, has a common mode rejection ratio of 110 dB, which is not unusual for a good quality op-amp, right? Better than the one of the mill ones that we have. 110 dB. So that's a huge number. If you want to find out what that really is, again, convert it from decibels to the real world. And remember, this is the ratio of AV diff to AV common mode. Ideally, this is supposed to be some value that we want, greater than 1, greater than or equal to 1. This is supposed to be close to 0. Very close to 0. So let's see what happens if I were to take this nice expensive op-amp and make a differential amplifier using 1% resistors, right? 1% are pretty good resistors. You get them in stores right now, and they are about the most accurate of those small little resistors with the color bands that you can get. So what I'm going to do is that I'm going to make, remember how we get the gain to be just RF over R1 is by we match these two resistors usually. So I'm saying nominally this is supposed to be 10K here, and this now is supposed to be 100K, right? So under normal conditions, if it wasn't for the tolerance, if I assume that the resistors were exactly 10K and 100K respectively, AV diff for this circuit is what? AV diff would be what? The resistors are matching. I'm just looking at the values. AV diff for this circuit, if all the resistors were exactly the values that they have here, AV diff for this circuit is going to be what? Come on. Once all the resistors are matching, AV diff is just simply 100K over 10K or 10, right? You know, we said that once you make the resistors, if you made these two match and you made these two match, then AV diff is simply RF or RG, whichever one, divided by R1 or R2, okay? So it's 100K divided by 10K. So if all the resistances were equal, the AV diff for this would be 10, and the AV common mode would be 0, right? So you could go back to the previous slides where we had the little the formula that we derived. So let's see what happens now. If for some reason this situation arises that RF and R2 are the nominal value, but they're on the high end. So they're plus 1%. Remember, they're 1% resistors. So that means that the value could vary between, in the case of R1, 10K minus 1% and 10K plus 1%. It could assume any value between that. And that R1 and RG, these two here, so these two go down. So R1 and RG go down by 1%, and RF and R2 go up by 10%, by 1%, right? This is also a pointer when you all later on, when you're doing circuits anywhere and so on, always measure the values of the resistances. And when you go into the stores or you buy components, you buy the components and you're going to read the color bands on it and say, right, this is a 10K resistor, 1% 10K. So I'm assuming that the value is 10K and I put it in the resistor, in the circuit. Remember, it does have a tolerance, and the manufacturer is saying that in a large batch of these resistors, on average, the value is going to be 10K, but it has a chance that the value might vary by plus or minus 1%. So always measure it. Yeah. Okay, 1 second. So cautionary point, always measure the values of the resistors. Don't assume that the value is always a nominal value that you see on the bands. So let's say the effect of this. So these two in red here, R2 and RF have gone up by 1%, and R1 and RG have gone down by 1%. You could do the calculations. So that they're not on the slide, so you do the calculations and then substitute now. If you substitute back into our, let me just stop it here for a second. Right. So if you substitute now into the expressions that we had a few slides ago, you can work out based on this. Let me just go back very quickly. Right. So you substitute here. So you can work out, remember this here, this bit here, this is AV common mode. And this bit here, the whole thing is AV diff, right? R2 and RF have increased in value, R1 and RG have gone down, right? That's what the particular problem is. Okay, there. So 2 and F have gone up, 1 and G have gone down. So you calculate the new value. The nominal value for R1 is 10K. So if it went down, right, it will be 10K minus 1%. You work out that. And the same thing for RG. RG is 100K minus 1%. You work out that. Then you put them into, you calculate now, based on that, you calculate AV common mode and AV diff, right? I'm leaving you to do that. So you'll be able to double check the numbers and see if they're correct. If you do that, you're going to get first that AV common mode is this value, right? The negative sign, it just happens that way. So the magnitude of the gain AV common mode, so it's a very small negative value, 0.03. AV diff is 10.184. And we said from before, for the 10K values that we had, the expected value was supposed to be 10. So the actual value is 10.184. So AV diff is a little bit higher than calculated. AV common mode, ideally AV common mode is supposed to be 0. It is not. It is a very small negative number. So what is the common mode rejection ratio? Remember that is 20 log 10 of AV diff divided by AV common mode. If you do that, you get, and you convert it, you get that the diff is, that the common mode rejection ratio in this case is 48.8 dB. Notice I had the op amp, or presumably the design, was using the fact that the op-amp came with a common mode rejection ratio of 110. I put in 1% resistors, which are supposed to be fairly good matching resistors, and they gain, the common mode rejection ratio has gone down to 49, approximately, by the mismatch of the resistor values. That is a staggering amount, because if you look at it, the difference between this as a real number and this as a real number is a huge difference. So in other words, if I bought this op-amp assuming that because of the high common mode rejection ratio, let's say I'm using it in a critical application, like a medical application, where I need the high common mode rejection ratio, but I put it in here with resistors that I'm assuming are matching because they're 1%, so I'm assuming that they're fairly close to matching. And instead of 110 dB, I'm getting 48.8 dB, about 49. That's worse than even a 741, right? And this would have been an expensive device. So just in sort of summary, if you want this, they sort of to see it, and there's a handout I'll give you all to read from a manufacturer. If you use 5%, we're on the same design that we have. If you use 5% resistors, the common mode rejection ratio is going to drop to just 10. Remember, it starts off at 110. 2% resistors, it dropped to 25. 1% we saw is 48.8, about 50, close to 50. 0.1%, well, you will get the 110 dB if you want. The theoretical value is 500, but the op-amp could only give you 110. So if you want to get the full 110, you have to have resistors that are matching or have a tolerance of plus or minus 0.1%, right? That is next to impossible to get easily. But from what you know, think a little bit. From what you know about your science, maybe some physics and maybe some engineering, how could I, if I have only 1% resistances, how can I improve the tolerance if all I have is a set of 1% resistances? You have any idea? Or from what you could recall, anything? Okay, one of the things you can do is to make up the value of the resistors by using series parallel combinations. So for instance, if I want a 10K resistor and I take two 20K resistors and put them in parallel, 20, 20, and put them in parallel, I am going to get 10K. But the error on this thing, if this was plus or minus 1%, this is plus or minus 1%. The parallel combination is going to give me plus or minus 0.5%. Right? When you put the things in parallel, you basically have the error. So what you have to do basically to get the kind of performance here is that you first off, you measure the resistances. The closer they match, of course, the better. So you pick 220K, like for this thing, 220K resistors, you measure it with a digital multimeter to get two values that are as close as possible to 20K. And then you put them in parallel to give you a 10K. And the tolerance, if they were originally 1%, the tolerance of the parallel combination now is going to be at least 0.5%. You're going to get better than 1% by putting them in parallel. This is all about errors, and if you remember when you spoke about these kind of things in your science, reporting values, right, and things like significant figures, all right? So to get around that, instead of trying to make the amplifier using discrete values of R1 and RF and so on, what you can do is, of course, you can purchase a commercial unit like the one here. This one has all of the resistors inside of the circuit, and the resistors are matched to these kind of tolerances. They're matched to like 0.1% tolerances or better. So this particular device is a ready-made differential amplifier. Notice that all the resistors are equal, so the gain of this AV diff is 1 for this, and they're telling you that the common mode rejection ratio for this is 86 dB. So if you know this, you could find out what AV common mode is. You could work that out and you could see how small a number it is. But this costs, right? So this kind of thing, you know, talking in the 10s and 20s of US dollars for a unit, okay? The other way to do it now is, if you look at this, we have a couple of issues with this. First off, the input impedance here, the differential voltage coming in here is seeing either R1 or R2 as the input. Those typically would be like 10 to 100K, which is fairly small. So the input impedance is a little bit low. And then if I wanted to change the gain, you remember we just saw all these resistors have to match. And then if I have to change the gain, I have to change at least 2 matched resistors. Remember these were the 100Ks here. This was the 10K here. So the gain is supposed to be whatever these 2 values are. They're supposed to be equal divided by whatever these 2 values are. So if I want to change the gain of this amplifier, I need to change 2 resistances, that is 1, and then I have to make sure that they're matched. Otherwise, I'm defeating the whole purpose of this, right? They have to be matched. So how we do this now, instead of going to that level, is by another configuration. We're going to add 2 more operational amplifiers to this and create an entire circuit. It's not a single device, it's a 3 amplifier thing that we call an instrumentation amplifier. And it overcomes all of the advantages here. 1, it has a high input impedance. 2, we can change the gain of it by just changing 1 resistor instead of 2 matching resistors. And then 3, it retains a very high common mode rejection ratio. Okay, and we're going to look at that tomorrow morning when we meet, please God. So any questions? You need to watch it. You need to look at the slides again and understand what we did. Fiddle with the calculations that that we had on the previous slides. Convince yourself of what we were discussing about the mismatch. The important thing is these, for this kind of application, it's a differential amplifier that we're looking at. So we want to amplify this and ignore this. And in order to do that, these resistors have to match and the tolerances have to be next to nothing. If they're not, then the common mode rejection ratio, which is how well we amplify this and how well we ignore this, is going to be low. Okay, so go over that, and then tomorrow now we're going to talk about the instrumentation amplifier in the first half of the class. All right, any questions? Comments? It makes sense?
So
yes.
Let's say they give us a run equal to 10K, right? With a tolerance of 1. So it would be 10 plus 0.01.
10K, and the tolerance is plus, okay, you say plus 1%, right?
Plus
so
1%.
Yeah. So it will be 10K plus 1% of 10K. So you should land up with what you said, 10 point what? 01?
01.
01K, right?
Is that right?
Right, and then if the other one is 10K minus 1%, right? You should get what, 9.99K or something like that, right?
Yeah.
Right? And same thing for the 100K resistors, exactly. So you use that now into the, to calculate both the common mode and the differential mode gain and see what answers you actually get. Yeah,
Yeah.
good. Any other questions?
No, sir.
All right. Okay, I'm going to stop the recording here.